when I was planning for this particular series of lectures, Frontiers in Combustion. So yesterday you heard Professor Sokolow talk about sort of overview of the landscape of energy and the climate. And so he started the whole series. Then I think the second one, a very logical one, would be the technological developments for the energy landscape. And then, right, the first person that came to mind was our speaker today, Dr. Jill Richards. That you will see what I mean. He's very knowledgeable. He is team leader at the DOE's National Energy Technological Laboratory, and they look into all sorts of different technological concepts. So I called him up, and he very graciously agreed to do it, and he has been spending a lot of time in putting this together. So I'll just leave you with him and enjoy.
All right. How is my volume up in the back there? I'm a pretty loud speaker anyway, but I know I was up there yesterday and a lot of white noise. But let me know if I drop off a little, like wave at me, because I want to make sure I get through to y'all. Well, I want to thank Professor Law for this chance to give a 3-hour talk. I'm not sure I'm going to do that, but anyway, we might truncate here or there depending on how the time goes today. But I struggled for a long time, and just so you know about me, probably to me the most important thing is what's on your first slide, right? Just that's the way I am. And so I was looking around for an image that I could use, and I run across this photo, this almost iconic photo of the Olympic flame. And we're going to see it in a few weeks. I thought, how appropriate, we're almost at the time when we're doing the Olympics. And I said, I got to use that because, well, it's a combustion group, right? And it's an interesting looking flame. You can see the soot going up in the corners. But also, I wanted to use it because I just thought it sort of captured some things, the spirit of those young men and women that are trying to do something really unique. They really committed themselves to their goal of competing in the Olympics. It's really, in some ways, like a lot of you, right? I know there's people sitting in this room, grad students, that are working just as hard as they can to learn their subject, go through the discipline of that, and then try and take that and do something significant with it. So I just want to encourage you on with that. Maybe when you see the Olympics, you'll say, hey, that's me. I'm working away here in my lab or working at the computer doing this. I'm just struggling to compete in this area, which I've chosen. Now, I put the slide up there, and I thought, okay, I have to maybe, I don't normally tell this. Modesty would usually forbid, but this is kind of a special audience. You want to know who your speaker is. And very few people know that I won a bronze medal back in '68. And the competition was fierce, but I took third place, the spelling bee at Worldview Elementary School. And that was the zenith of my literary career. I realized after that I was headed on a technical track. Linguistics wasn't my strong suite. So anyway, with that, by the way, I don't think Professor Law knew the true caliber of his invited speaker here today. And probably if he did, he would have had second thoughts. But anyhow, we'll keep going here. All right, I'm going to give just a few introductory slides here. Some of this overlaps well with the comments by Professor Sokolow tomorrow. I've used this slide a couple different venues just to make the point, something that you're all aware of. Electric power is pretty important to the developed world and to the world that's yet developing. And you can see the outline in that image of the places where we have good access to electric energy, efficient, clean energy. And it just makes the point that there's a lot of places in the world where we don't have that access. And I didn't make this statement. You can look down there. This was a guy, former chief technology officer at Microsoft. This is the biggest problem we have in this century is how to get every citizen of Earth roughly the same per capita energy that we enjoy in the developed world. And use that word enjoy, and it almost sounds indulgent. You say, I don't know. He's not talking about enjoy like I enjoy eating ice cream, right? I mean, energy is important for things like getting clean water, for having access to decent health care, to having a clean environment, to heat your home. All those things built on having access to clean energy. So I made a statement earlier. We're all combustion people, but really we're energy people here, right? Very important issue. You know, I have friends that are serving as missionaries in West Africa there. They've built a hospital in the middle of nowhere. Look at how much electricity they have. It was just remarkable to me the difficulty they had putting an operating room together. You think about that. You're trying to run a respirator with a patient on the table. You don't have access to reliable energy. Maybe he does have a point here. It really is a big, gigantic issue of how do we improve access to clean energy around the globe. This next slide makes this more quantitative. It's a plot of per capita GDP, gross domestic product, and you know, it blows my mind that that's on a logarithmic scale up there. And then also on a logarithmic scale, energy consumption on this axis, that's kilogram oil equivalent per person per year, and you can see the relationship among all those nations, the developed nations up in here, and then you go down further, and I think, you know, the point I made earlier, these folks want to have that energy, not just to enjoy it in an indulgent sense, but so they have access to health care, education, lighting, heat, all the things that we value so much for a decent quality of life. The other thing that's interesting about this slide is, look at where some of the large populations are today, and they are developing. I think you can conclude immediately there's going to be a big increase in the demand for energy as those nations develop. It's unavoidable. And so our mission is to try to improve access to clean energy. And combustion, of course, a gigantic part of that. You know, you look at that last slide and you think, well, you know, I'm just a graduate student. I'm trying to do research on a diffusion flame. How can I have any impact? Let me tell you, you can have an impact. All right, I wanted to put together probably the best example I could find. And it's it's our own laboratory, my laboratory. You've probably heard about shale gas. Raise your hand if you know what shale gas is. I got to make sure I know who I'm talking to. It's transforming the energy industry in the United States within the last 5 years. Been huge, huge development of the shale gas resource. Much of it right in the area, right where I live. Here, we're over here in New Jersey, PA, West Virginia. That's the Marcellus Shale Formation. Do you know why we're able to extract so much gas from that formation? Because of work that was done in our laboratory back in the 70s and 80s, advanced drilling, horizontal drilling, being able to steer a bit and run through a formation horizontally, and then at that time it was called stimulating the well. Today we call it fracking. That was stuff we were working on back in the 70s and then on in the early 80s. Some of the people that I started my career with that have now retired were developing that. I talked to one last week, talked about his experiences. What an achievement to think, you know, that work we were doing that frankly not a lot of people were paying attention to. This, oh, it's too costly, it's too complicated, it'll never work. It's changing the energy industry today, all right? Now, we kept working on it, and frankly, on not a lot of funding through the middle years there, looking at where were the geological environments where this would work out. There was work going on, and then finally it's just taken off. Whereas you look forward in time, look at the percentage of natural gas we expect to be supplying from those shale resources in the years ahead. It really is changing the energy industry. Today, our lab's focused on making sure we can recover that resource, guaranteeing environmental sustainability. We don't have any problems with recovering that resource. So we're still working on that. But look at the time scale, 30 years. It's amazing. But look, I'm putting this slide up because many of you are working in energy, thinking, how can I have an impact? I'm trying to put forward a couple ideas. It takes a while. It's not always going to be people saying you're working on the right thing. That's what's happening back here. But it pays off eventually. It really does. So I want to encourage you, keep going on that research you're working on. All right? You might think, oh, Gio, you picked an example here. These guys, they had it made. They were looking at something to supply a brand new fuel source. That's going to have a big impact. Well, let me give you an example. You think, well, my combustion design, I can't have that big impact on fuel supply like these guys did. All right, when I leave on Friday afternoon, drive back to my house in Morgantown, it will take me almost exactly 1 tank of gas in my little 4-cylinder truck. It'll just about be on E when I get there. All right? Somebody in this room is probably working on an HCCI engine that in 20 years, I'll be able to take that same trip, and by the time I get there, same horsepower engine, I'll probably have 10 or 20% of that gas left. So now I get there and I open the tank and I look in there, you know what? I just discovered a new energy source, didn't I? Is there something wrong with that logic? It's a new energy source. I try and get this point across to people that I talk to. Efficiency in conversion is a new energy source, and yet it's lost in much of the discussion today about energy. People aren't, they just say, well, no, I've got to go find more wind or more photovoltaic or more shale gas or whatever. And it's like, the answer's right here for us is to focus on that. So I wanted to stop and make that point because I'm going to talk a lot about efficiency today. So I hope you remember that example when people say, what are you working on? Don't tell them you're working on a diffusion. I'm working on a new energy source. Efficiency, all right? Does that make sense? Interact with me a little bit because I want to make sure you leave with that point, okay? Everything else you might forget. You can't talk about energy today without also discussing carbon dioxide. And, this has been touched on a little bit yesterday. You can capture and store carbon dioxide from stationary power plants. We'll talk about that a little bit. If you would have asked me 3 years ago, I would have said it's going to happen, all right? Today, it's not so obvious we'll be doing this in the near term because of changing economic conditions, and there is actually a lot of debate on storage. Last week was congressional testimony to really question some of this. I don't know if that's the right testimony or not. I'm just telling you, this is in the middle of the crosshairs right now of a huge national debate. So will we see carbon capture and storage? I don't know. But something that many people are not aware of, carbon dioxide is a valuable commodity today. It's used widely for enhanced oil recovery. Did you know that? If you knew that, raise your hand. I just want to see. There's a few people that are aware. It was mentioned yesterday, just a moment. But you might not be aware of how significant that use is. In 2010, 58 million metric tons of CO2 were supplied to operating oil fields. 58 million metric tons. That's the equivalent of about the CO2 emission of 15 coal power plants, mid-sized coal power plants, get the CO2. You know where they got the CO2 to supply that? Anybody want to take a guess? Where does it come from? What's that? Some from stripping it out of natural gas, all right? That turns out to be just about 13% of that supply came from natural gas. That's the green dots that you see here. This one in particular is one of the larger ones up in Wyoming. They produce natural gas with it comes out of the ground, a lot of CO2, and then they have to strip it out, and then they supply that through a pipeline several hundred miles down to the oil patch. Can you believe that? The huge CO2 pipeline is running across the country. We just built another one right in here to get out to the West Texas oil patch. So you get some of that CO2 from natural gas production, but you get the bulk of it, the blue dots, from natural sources. Meaning you drill a hole in the ground and you get CO2 out. When the first time I heard that, I thought we've got all these people that are worried about CO2, and here we're struggling to get enough of it to go to enhanced oil recovery. Well, it just begs the question, why can't we take some of the CO2 that we're worried about and put it down those holes? And here's the answer. It costs a lot more to do that today, to capture CO2, than it does to just drill a hole and extract it out of the ground. So the question for us is, what can I do to develop an efficient and an affordable method to actually supply CO2 for enhanced oil recovery? Even if we never get to the point where we mandate CO2 capture and storage, I need it for this application if I can develop the technology. Should we decide we're going to store CO2 on large scale, you'll have something that works. It's affordable. So there's a little background on CO2 capture. And on this slide, I just want to, I've asked the question, can we develop affordable methods to capture CO2? Well, this slide covers the four major ways that you could do that. And I want to caution you, there are a whole bunch more. All right, I just don't have time to go into them. There's some really innovative ones we couldn't cover today. But let me go over these major ones real quickly. The first one is just to add a scrubbing system downstream of an existing coal power plant. For example, you can do it somewhat on a natural gas plant as well. But scrubbing is done with an amine compound, and it costs a lot of energy to take that CO2 out of that flue gas stream. In fact, this study kind of surveyed all the reports and studies. The efficiency of the baseline power plant could drop by 25%. By 25% of the original, by which I mean like if it was a 40% efficient plant, it it would drop to 30%. Okay? So that's a pretty significant hit on plant efficiency, and it means you're using more fuel to do the same job, right? But you can do that to capture carbon dioxide. There are a lot of people looking at that right now. You could also go before the combustion process. This is again with coal here. You gasify the coal to CO and hydrogen, cool it down, and then go through the water gas shift reaction. And you separate out the hydrogen that's left, and then the turbo machinery, the engine becomes a hydrogen turbine or a hydrogen engine, and so you have the CO2 which you can send to enhanced oil recovery or sequestration. The efficiency of this process, depending on who you ask, it also takes a pretty big hit. It might not be quite as large, but it's not substantially better. Big efficiency penalty for CO2 capture using that approach as well. Or you could go through oxy-fuel combustion. Here you take the nitrogen out of air, so you're left with oxygen, run it into the power plant, then the product stream is just CO2 and water. We're going to talk about that in more detail here in just a second. And it's a nice process, but it turns out the cost of getting that air is so large, the efficiency penalty is about the same as what you've got up there. And so I have those three options, and one might be a little better than the other, but there's no clear winner, which leads me to my fourth option here, something called chemical looping combustion. And I hope you are just dying to hear about chemical looping combustion today, because I'm going to be spending about an hour on it, and if you're bored with it, just pretend that you're not, so I'll feel better, okay? That's my only request of you here today. So here we go. You're going to learn about chemical looping combustion today. Before I get into that, I'm going to use this slide a couple of times through this talk, because I just want to put in context the importance of efficiency in two dimensions. All right? This is just sort of a simple block diagram. You could, whoop, no, got to back up here. You could do a heat and material balance around a generator, and you could write out an expression for the overall efficiency of this process, where I'm starting with fuel, heat going into this generator. I produce some gross work at this point. Then I have to spend some energy to take the CO2 out of the exhaust stream somehow to produce the net work. So I have an overall efficiency which accounts for the work that I have to do to get the CO2 out. Well, if you just balance those things out in two lines of algebra, you'll find out that the overall efficiency of that process is the generator efficiency, the primary generator here, minus this term, which includes omega, the specific work that it takes to separate out a kilogram of CO2. And then alpha is how much CO2 is produced for every mass of fuel that you burn. Okay, so I think that expression, it just makes sense, right? If it takes me a lot of work to pull 1 kilogram of CO2 out of that stream, it really hurts the efficiency of the whole process. The point is, most people today who are thinking about carbon capture, they really focus their effort and their attention over here. How do I get the efficiency penalty down from this process? Most of the processes we look at today, 6 to 10 percentage point penalty. Huge. So it makes sense to ask, what can I do about that term? But it sometimes gets lost. This term is sitting there too. And even if I could bump this up substantially, I'm going to show you a way we might do that, I might be able to offset that term. That's the hope. That's what I'm going to show you why something you combustion engineers can do to actually make that kind of a jump. So again, my key point here on this slide, reducing that penalty from carbon capture, it's a function of both the base generator efficiency as well as the efficiency of separating the CO2. So remember this slide, we're going to come back to it a couple more times. All right, so here it is. Today's presentation is supposed to be new combustion technology or something. There's a title there, New Approaches. I'm going to make an Olympic effort here and try and cover 3 ways. I'm not sure we'll get through all 3, but we'll give it a shot here. 3 different ways we might do that. 1, chemical looping, I've already described. A second one, a step change in generator efficiency, pressure gain combustion. And a third one we'll keep as a surprise. How in the world will we make oxy-fuel an advantage? But we're going to show you a way you might do that. Anybody here who is a lawyer or a friend of a lawyer? Okay, we feel sorry for you, but anyway, I'm teasing. So to just show we have something for everyone, okay, our agency, of course, insists I add this important piece of information in all talks that I give anywhere. And you can read all that long text. I like to describe it this way. You can't blame the government for anything you learn from me today. So don't even try it. Okay. All right, let's jump right into the technical details. I've wasted too much time already here. Oxy-fuel, all right? Described this already. In conventional air combustion, I'm representing, this might be like a coal chemical formula, CH, one carbon, one hydrogen. In conventional air combustion, you burn that to produce CO2, water, and then there's a lot of nitrogen in there. And this is what really makes it complicated to pull that CO2 out in a scrubber, because you've got all that other gas. It's a very dilute stream, and that's where all the energy goes. Oxy combustion, if I can get pure oxygen, good idea, right? The products are just carbon dioxide and water. And so separating the CO2, very easy. Just cool it off, and there's your CO2, right? You condense that water out. All right, so the usual approach to doing that is you dilute the oxygen with either CO2 or water to keep the temperatures reasonable. You don't want to make a cutting torch, and then use an existing cycle to actually operate the process. And the efficiency of the whole system is penalized by the energy that you need to make the oxygen. Everybody understands that. There are some very significant demonstrations going on of this technology in spite of that efficiency penalty. I gave an example of some of the university work, great work going on here at University of Utah. The Department of Energy is sponsoring the ever-changing FutureGen. It's called FutureGen 2 right now. A big oxy-fuel plant planned for Illinois, and there are other places around the globe. You can go look at that if you're interested. More than 10 demos, greater than 10 megawatt thermal. So a lot of interest in oxy-fuel, but it comes with a big price tag. You have to make the oxygen, all right? This isn't cheap or easy. I'm showing it schematically. Here you start with a mole of air, run it through an air separation unit. Large scales are typically cryo units. If you just calculate the reversible separation work to separate that into two streams, it's about 6 kilojoules for every gram mole of oxygen that you make. In actual practice, the best numbers I've found in the literature today is about 3 times that. Okay, so that's how much energy it takes to run that separation unit. And you can just do a quick calculation. You don't normally have a power plant using pure carbon, but anyway, just to make it simple, we'll look at carbon combustion with 1 mole of oxygen gives you CO2. The heat of reaction, it's not much different than the change in Gibbs for energy there. It's almost 400 kilojoules per gram mole of heat released over here. And in really the best power plants, maybe half of that, probably less than half of that's going to be turned to work. So about 200 kilojoules per gram mole of oxygen, work being produced by burning that, and I needed 18 kilojoules to make the oxygen in the first place. You see where the math is going here? It takes like about a tenth of the power plant output to make that oxygen. It's a little bit better than that in practice because those plants have hydrogen in the fuel, right? But I'm just trying to make the point, separating oxygen from air costs a lot of energy and money for the cryo plant and so on. It's a big issue, how much energy does it take to make oxygen. So can we do something different that still captures the benefit of oxy-fuel combustion, but I don't need to make the oxygen? Well, that's the promise of something called chemical looping combustion. Again, the products are just CO2 and water. You don't have a separate oxygen production. And this is the way that it works down here schematically. This is a circulating fluid bed reactor. And what I'm showing up here in that orange or yellow region, you can take a hydrocarbon fuel and put it into this bed of material, which includes a solid metal oxide. That metal oxide will give up, with the right metal, give up that oxygen to burn the fuel. I'll be left with carbon dioxide and then the reduced metal. All right, so now what do? I take that metal, the reduced metal, out of here and react it at high temperature with air. I'm essentially burning that metal. All right, then I bring it back around here. I now have the oxide again to go in, and I'm supplying the oxygen to my fuel reactor. If I did all that, the product stream is just CO2, and if there's hydrogen involved, water as well. Okay, does that make sense to you? Please make sure I got this point, or you'll really be bored. Everybody on board with me on this? Okay, how it works. Okay, there's chemical looping. That's how the process works. There's a lot of interest in this worldwide. I'll show in just a moment some sketches of different reactors. There are other schemes for hydrogen production that I won't cover today. There's even an interesting one for carbon capture, but I'm just not going to have time. Go ahead.
So all the oxidizing from metal oxide.
That's right. Yep, you'll see how this works in just a second. Almost too good to be true, but that's how it works. Let's just take a look at, the fact that this is supposed to be new technology. Well, it's not quite new. It's been around. The drivers and the context are quite different. There's a patent that goes back to 1954. I took this sketch out, and these guys, it was for a chemical company. They were interested in producing pure carbon dioxide for some chemical purposes. And you can see in here, it's the process I just described. The fuel goes into this reactor. The metal oxide, which I've colored red here, reacts with the carbon fuel to give you CO2, and then the blue is the reduced metal. That reduced metal then goes through this reactor, where it reacts then with air to give you the metal oxide at this point, and then that metal oxide is then cycled back through the other reactor. Okay? So just so you know where we're going, pay attention to what I circled on that diagram. You see those two yellow things? There's two heat exchangers in there. Okay? That'll be important to remember that part later on. This isn't the first time people thought about something. This didn't have the name chemical looping, but very similar was the iron steam process to produce hydrogen. That goes back even earlier, back into the 20s. And the process, it's not a combustion process, but again, you take hematite reacted in this case with carbon monoxide, you get an iron right there. So again, you're reducing that oxide, there's the CO2. Then you take the reduced metal, the iron, and react it with water. And of course, then the oxygen goes over to the metal, and you're left with hydrogen. And that was a common process in the 1920s for producing hydrogen. And so we're sort of going back in time here. So before that, there's respiration, right? And you understand how that works. It's chemical looping. I'm breathing in, that oxygen is oxidizing the iron that's in the hemoglobin in my lungs. It then goes out and does hydrocarbon combustion, really, to produce the energy that I need. And then that CO2 goes back out through your lungs, a different chemical process there as well. I was trying to find who had the patent on that, but it didn't show up in my search. So anyway, go ahead.
So why metal oxides?
Why metal? Oh, we're gonna cover that. It's not restricted to metal oxides. You'll see some more here in just a second. A lot of people are looking at this right now. A lot of interest. I took these two things on the top here from a great talk by Henrik Leon and then the late Adel Seraphim just about a year ago in Clearwater. And first of all, a number of people looking at CLC as potentially become preferred option for steam boilers. Remember that thought. We'll get back to it. For steam boilers is what they said. We'll get back to that in a moment here. But then these guys looked at power generation from an Oxy-fuel 600 megawatt pulverized fuel coal plant, integrated gasification combined cycle. So this is pre-combustion capture. They calculate the energy penalty of removing the CO2 versus some baseline, 20% energy penalty. Look at that. And then they said, let's look at chemical looping combustion. CFB combustor, 4%. Whoa, if that's right, that's a huge improvement, right? I'm really interested in understanding, can I do this? And the cost, again, cost of CO2 that's produced much, much lower. So the question is that really right? Can we really build devices that are like that? There's another quote down here for gas turbines that I won't take the time to go through today. But again, a lot of people looking at this in different parts of the world. We've talked to many of these folks and have different kinds of interactions. Maybe I've missed somebody here domestically. If I have, please let me know. We'd like to talk to you. We're trying to really provide leadership on this topic. We've been talking with some people at Utah as one example and other places. This slide shows different groups that are working on this domestically and different universities. Alstom is one of the few U.S. entities pursuing this commercially. It's interesting that all the universities that are working on this, they're all located right near places where coal is being used. Isn't that interesting? But I'd like to see that grow. So you guys, they're from the California schools, come on and work with chemical looping combustion. That'd be great. Let's get into the details of chemical looping combustion, starting off with just some basic concepts for thermodynamics. The idea, again, I'm just using coal. This could be any hydrocarbon, or carbon. It could be coal. It could be any hydrocarbon. We want to react with oxygen to produce CO2. and there's some heat of reaction connected with that step. You can break that down into the two chemical looping steps, right? First, I react the carbon with the metal oxide to reduce the metal, then I take the metal and reduce and then oxidize it to get back to the metal oxide. And obviously, the heat of reaction of these two has to add up to the one on the top. That's how it works. A key point here, which first time I started reading this, it took me a while just to notice this. This doesn't have to be exothermic itself, right? This one can be endothermic or it can be exothermic. The two of them have to add up to give you an exothermic reaction, right? So you're going to see that as we move through these talks. For some of these metal systems or sulfate systems, whatever, some can actually be endothermic, but then you have to make the heat up in the other reactor. I think I'm connecting with a few people who are following me on that. So let's look at potential oxygen carriers that have been studied. And this was the question that was asked. I'll get to that in a second. Does it have to just be metals? And there's a whole list here. Professor Phan's book from Ohio State is a good reference. It just came out fairly recently, and so I put a lot of the slide together from a couple of charts he had there. But you know, a very common one we're interested in is just plain old iron in its different oxidation states. And a key point you need to understand is some of these metals have multiple oxidation states, like iron, right? It goes through iron 3, 2, 1, and then just iron. So that makes it an interesting problem to understand how it's going to react in the system. Copper is another really good one. It has 2 oxidation states to get the oxygen off. There's a lot of literature on nickel, and you know, those guys are really brave. I don't want any nickel powder in my lab. It's just too hazardous to work with. So we're not looking at nickel in our lab. For people that are, I'm sure they're taking the precautions to use it, but we haven't done much with it. You go down the list here. Here's some of the other ones. The sulfate-sulfide transitions. This one here, calcium sulfate to calcium sulfide. Lots of oxygen on that molecular compound coming off every time it goes around the loop. It's a good oxygen carrier. Has some issues with maybe stability when you go to use it, but that one's being pursued pretty aggressively by Alstom for coal applications. So let's look at some of the thermodynamics just for iron and copper. I don't mean to exclude the others, but these are the common ones people are working on. So if I was going to use methane as the fuel, I have this overall exothermic reaction for burning methane. And then if I use copper as my carrier, I have 2 oxidation states where I can reduce that metal, go to cupric oxide over here, and finally down to copper, producing CO2 in both of those things. And then finally, I need to reoxidize that copper to get back to copper oxide. Interesting enough, for copper, all those reactions are exothermic. You know, you add them all up to get back to the heat of reaction for methane, but they're all exothermic. So it's an interesting thought. Hang on to it for a second here. If I go down to iron, all right, all of the steps where iron is being used to supply oxygen, they're all endothermic, all right? So there you got to supply heat, you know, to react the fuel with that metal oxide. And then when you go over to the oxygen reactor where you're reacting there, boom, you get a lot of heat released, right? So you burn that iron and then take the heat over to the other reactor. Okay, so now I got to see if I'm communicating well. So with all I've just told you, what large difference in system configuration has to exist if I'm going to use a copper carrier versus an iron carrier? And you know, I already gave you a bit of a hint there. What's the difference got to be? That where you got to take heat out of both reactors if you're using copper. If you're using iron, you better make sure you brought enough heat back over with the carrier to go into the fuel reactor, or it'll go out. Right? It's a very interesting problem, you know, as a combustion engine. I never ran into something like this where you got to think about how I'm designing the gross system parameters depending on my choice of reactants. But that's what you got. And so it really drives the system configuration, the choice of the carrier. Right? How is it going to behave? So we're going to spend a little bit of time talking about, you know, some of these carriers. Before we do that, you also have to deal with the issue of the thermodynamic limits for conversion. Right? Because I'm saying I want this thing to be a combustor, to create heat, and to produce CO2 and water. Well, you know, if I was going to supply the CO2 to enhanced oil recovery, this is a spec sheet that we're using that says in the flue gas, how much oxygen can I tolerate, how much CO, how much hydrogen can be in that stream. Well, I haven't even started to think about, well, how well can I convert fuel with that metal oxide? need to answer that? Well, that's an equilibrium question to get started here. Let's take a look at it, and just need to understand how this equilibrium works when you're trying to burn fuel with a metal oxide. All right, so here's a sketch of a partially used up oxygen carrier, metal oxide next to some metal, and that metal oxide metal pair at a given temperature obeys the equilibrium that I've got written down right here, equation number Roman numeral I there, 1. And what it's telling you is there is a partial pressure of oxygen where this is at equilibrium at any temperature. So at 800 degrees centigrade, there is one partial pressure of oxygen that puts that system in equilibrium. If I drive the partial pressure of oxygen higher than equilibrium, PO2 star, what happens to that system? If I've got a lot more oxygen, what's going to happen? You'll oxidize the metal, right? This thing will start to grow and that'll shrink. If I drop the partial pressure of oxygen below it, what happens then? It goes the other way, right? That's the equilibrium. It's that simple. So how do I control the partial pressure of oxygen over here? With the fuel, right? That's what combustion is doing. It's trying to reduce the partial pressure of that oxygen, and as it does that, it pulls the oxygen off into that reaction set and leaves the metal behind. Okay, so that's how the equilibrium works in these systems. And if you're patient tonight, you can just sit down, and I didn't put the numbers in here, but if you got a table where you can look up the standard Gibbs for energy, you can calculate those ratios, you can figure out what that is, you can see right where does the equilibrium sit. All right, so now here's the quiz for you, all right? So suppose you start working this area, and you're building your chemical looping combustor, and you've got 30 ppm of CO, and your professor comes in and says, we can't have 30 ppm of CO. Why don't you add some more metal oxide to it? You don't have enough metal oxide. Is he or she right? What do you think? By the way, when I take multiple, just somebody told me, always go with your gut feeling, right? But right. So is that right? Adding more will get rid of it? Yeah. Yeah, if you didn't have enough, right? If you didn't have enough. That's the caveat, right? For some reason, I found this conceptually hard to accept. Think about it. You can have this as much surface of metal oxide as you want. You aren't going to change PO2 above it, right? It's only going to do what we said if you didn't have enough metal oxide. So the correct answer is, of course, maybe. See, I had a law background, no, right? It's maybe because you don't know what's limiting it. But the point I'm trying to make is, if you're already at equilibrium, you can add as much metal oxide as you want and nothing will happen, right? That's the nature of this heterogeneous equilibrium. I'm looking around, I'm kind of picking up a couple people like this and a couple people like this and a couple are saying, I just want to graduate. Come talk to me at the break, we'll work it out from there. Not the graduation, the details. All right, so here's actually a calculation here just showing what I just told you. All right, so here's the residual concentration of CO plotted against temperature. This happens to be hematite to magnetite, 2 states of iron in a hydrogen or in a CO mixture. And what you can see is you go up in temperature here, and the residual hydrogen levels drop off, the CO levels start to come up. This has to do with whether they're exo or endothermic. But for the temperature range where we're going to operate, I think it's fair to say you probably aren't going to do much better than about 40 ppm of either CO or hydrogen in the product stream. Interesting, you probably have less to worry about in terms of oxygen. If you're going to supply CO2 to a pipeline, don't put any oxygen in there, right? That really corrodes the thing quickly. You don't have any here, right? So you could probably put up with this level of CO and hydrogen if you're going to sequestration. If you're doing something else with it, you didn't want that much CO2, frankly, you could bleed in just a tiny bit of air and you'd probably take it all the way over. Then you'd have a little bit of oxygen, a little bit of nitrogen. Okay, so that's equilibrium. What are we doing time-wise here? Solid carbon formation, is that an issue? Let's see what's going on here. Here's, again, this oxy-fuel combustion loop. So suppose I don't do a very good job in this fuel reactor and I have some carbon left on my oxygen carrier and it goes over to here. What happens to the carbon? What's that? I can't quite hear you. It'll get burned in that air reactor and go out as CO2, right? So it wrecks your whole hope that you're going to get like CO2 in one reactor. It ends up coming out of the air reactor, right? It can, I think you said follow it up. I apologize, it's really hard to hear. And yeah, you have to worry about carbon formation, not just by equilibrium, but by cracking, and then you can follow it up, to use your phrase. You're absolutely right. It's probably not much of an issue to worry about carbon formation in the reactor itself. I just plotted up the Boulard reaction here, and there's the line where carbon will form with a high enough CO level on that side, or you'll gasify it to CO over on that side. Probably not too worried about that, except maybe in some parts of the system. But a key point I want to leave you with is, even if you form carbon on the metal oxide, is that a problem? Probably not. It's trying to react with it. I'll show you why in just a few minutes. Right? If people looked at this process, oh, you're going to form carbon on that oxygen carrier, you're going to get all gunked up or whatever. Won't happen that way. Why? Because the oxygen is sitting in there favorably wanting to react with that carbon. Now, if you use all the metal oxide up, good luck. It will form a lot of carbon. And that's where this question before, I said the answer is maybe. If you don't have enough, you better put enough in there to avoid carbon reacting on iron. That's a great carbon former. So you got to avoid that. All right? So I hope I've given you some things to think about there. Let's talk a little bit about oxygen carrier capacity and circulation rates. This slide just gives you the nomenclature that we'll need here. This is a representation of a carrier, and a lot of these carriers, you have an active species. This is the metal. It's going to become a metal oxide, and it's sitting on maybe inert support. It doesn't have to be. Sometimes you can have pure metal, but we just need to define that this is the state. If I take the mass of the active species minus its reduced state, in other words, what I start with here, then divide by the mass when it's fully oxidized over here, minus its reduced mass, that gives me this quantity X, which is the conversion, right? So the fully reduced material has X1, and the fully oxidized, I said it backwards, the fully reduced material has X0, the fully oxidized material has X1. Okay, so from 0 to 1, just a convenient way to tell you how much of that carrier you're using. It doesn't have anything to do with how much inert is present. And then you can develop some other nomenclature that's going to be a little bit useful. That's X I just described. This is the oxygen transport capacity, basically the difference between the mass of the carrier when it's oxidized minus when it's reduced, divided by the initial oxidized state. So this is telling you how much, what fraction of the mass of the active material is going to supply oxygen, right? So if I say I have an R0 of 0.1, let's say I have a kilogram of material with 0.1 value of R0, how much oxygen can I get off of it? Can you answer that? I have a kilogram material, R0 is 0.1, how much oxygen could I get off of that? Say it good and loud. Oh boy, I'm losing you. Maybe it's time for our break. How about it? Actually, I don't know what time I'm supposed to break. Oh, man, this could be okay. Do me a favor, just stand up for a second, stretch. I don't want to lose you on this point. Just take a quick break here. I don't normally give the lecture 3 hours long. I don't know if that happens at your university. It's really a challenge.
You hit the camera?
All right. Doing okay? Get you focused here again. So let me try one more time here. See if we can, now that we're at a quick break here, just try and see if you can answer that question. So this R0 quantity, oxygen transport capability. The difference between the oxidized mass, the reduced mass divided by what you started with when it's oxidized. So let's say it's 0.1. 0.1. Suppose I had a kilogram of oxidized material. How much oxygen could I get off of it? 0.1 kilogram, right? It's real straightforward. It's just a fraction of that oxidized material that can go to oxygen. That's all it is. All right, so telling you how much oxygen can come off the system as you go from oxidized to reduced state. Here's a couple other parameters here we won't need, but they're there in your notes, and you can go back, and I drew a picture. You can actually work out what they mean, but we don't need them today, so I'm going to skip them. But I wanted to make sure you understood what this oxygen transport capability is, because it's so critical to your selection of oxygen carrier. So for example, probably the most inexpensive carrier is iron when you go from, this is hematite to magnetite, and that value of R0 is 0.034. In other words, 3.4% of the mass of your iron oxide will come off as oxygen. Boy, that doesn't sound like a lot, does it? But that's what the number is, right? And it's a property of that metal oxide-metal transition. And so you can write down R0 for a lot of different systems that you're interested in, and you can go right down the line here and start. I range them from low to high. You can see different values here. If you take that original iron and go to the other, a lower oxidation state, you get up to 0.1. That's maybe a pretty good oxygen carrier, 10%. If you keep going and you look at copper oxide going all the copper, that's 0.2. So now I got 20% of the mass of that material going around to become oxygen. And then if you go down here to calcium sulfate, going to calcium sulfide, it's almost half the material mass can come off as oxygen. So that's a really appealing oxygen carrier because you don't have to circulate as much stuff around, right? Does that make sense? The difficulty is every one of those has to have long-term durability. Because, I mean, there's other factors besides just their oxygen capacity when you start looking at picking them. How much do they cost? How durable are they? Will they work in my system hydrodynamically? There's a whole bunch of issues we'll get into. But so you go down this list and just think about what you want to pick. All right? So this chart tells you the oxygen capacity that's available to you on that carrier. All right? So let me give you a little test to see how well this is going. Oh, go ahead.
Does this property change with temperature?
No, it does not. It's a fundamental property of the material, right, of taking it completely from an oxidized to reduced state. But if you reach equilibrium, then you're right. You see what I'm saying? I mean, because equilibrium will not let you take it to the oxidized. It's going to go one or the other. But you get to a certain temperature, you can't take it over because equilibrium is trying to push it the other way. We'll get to that for like flow. We'll talk about what that means in just a minute here. So let me ask a question now. I'm going to pick one of these oxygen carriers. Let's pick this one down here. R0 is 0.1. All right. So now I'm going to go build a system that actually is a combustor with that material with R0 of 0.1. I'm going to say, in my system, I want to circulate 100 kilograms per second of oxygen carrier. 100 kilograms going around the loop per second. So how much oxygen can I supply if I've got 100 kilograms of that material going around? How much oxygen? 10 per second, right? So if I know I got 10 per second of oxygen, the next thing I say is how much fuel I can burn with that, and I know the heat output of that boiler. You get all that? It's very straightforward. No deep math here or anything. Go ahead.
How do the kinetic waves compare from this carrier?
We're going to take a look. We're going to take a look at that in just a second. So hang on. We'll get to kinetics shortly. But I want to just make this point about capacity, because capacity is not kinetics. I just said, okay, that with my example I gave you, I can get to 10 kilograms a second of oxygen. That gives me a thermal output. But it doesn't say anything about how big those boxes are that it has to go through. How long do I have to keep it in a box while I'm circulating it around? Let's see that here on the next couple of slides. So let's figure out what we might do that's realistic here to actually build one of these systems. And this is how we did it at our lab to get a first crack at designing one of these. This is a FCC catalyst. You can see, okay, so FCC is fluid catalytic cracking, and we've got a number of chemical engineers I've met here in the audience today. The idea is you put oil in here, it goes on to a catalytic reactor, it does a cracking reaction, and it forms a lot of carbon, and then you take that solid catalyst and then run back down to this bed where air goes through, burns off the carbon, and then you recycle that catalyst around. It's a lot like chemical looping. It really is. This is known technology. It's being used, all over the world, and it circulates a lot of material around that loop. So we said, look, I don't want to reinvent the wheel. What can I do practically for chemical looping that's at least in the same scale of that circulating solids? All right. So we went out and we said, let's look at kind of a mid-size, maybe a little bit bigger than mid-size FCC catalyst cracking system. And they build these things that circulate even more, in fact, 4,100, 41 tons per minute of solid moving around that loop. I just told you, if I know what R is, the capacity R, that means I can tell you how much oxygen can come out of that process of going around that loop. You just did the example with me, right? So I said, all right, let's take a look for some of these different materials. How much thermal output, again, that's reflected by how much oxygen can come off that carrier as I'm going around and around that loop. And what we did is we plotted it up for some of those oxide systems that I just described. Here's the first one. This is the thermal output you could get for a system circulating that much material where you have iron 3 going to iron 2. Right? Well, it's actually not too bad. It's, maybe 350 megawatt thermal. Pretty big power plant, really. And then we just said, all right, well, let's take a look. If I don't fully convert the material, in other words, I'm just going to get a partial conversion of that oxygen, we'll plot up the same results over here. And pretty soon you start to see we're talking about, for some materials, fairly small, power systems, less than 100 megawatts for this particular transition. If I'm willing to use something like, where's copper? Copper is great, right? If I go from copper oxide to copper, we're talking about 700, 800 megawatts power. Look, the message I'm trying to leave with is it's reasonable, right? It seems like you could build a reasonable scale power plant circulating solids at a rate that's comparable with things that we already know how to build. This was always a criticism as we tried to get into chemical looping. Oh, there's so much hot solids going around. Well, we already do that in these systems, and we're proposing to do it at the same scale, right? So it's at least doable. But I'm not done yet. I haven't said anything about, somebody asked about kinetics, so we're going to move on to that here in a second, because although I can circulate that much material, that doesn't say how long I have to keep it in a big vat on either side, right? The kinetics determine that. I don't want to discover that it has to sit for a half an hour here, then go through a little transfer tube over to the next one and take another year in the other reactor. So we have to look at kinetics. So this is now gets more familiar to combustion scientists. Kinetic rates and reactor sizes. This is just an example of a bubbling fluid bed. It really, you put air in the bottom of the thing. There's a solid material in it. It will fluidize. We'll show some of this in detail in just a moment here. But it behaves much like a circulating or a stirred reactor bed. Air is moving through that bed. You put in a carrier at the top, and then it, in some designs, then it would come out the bottom as you try to oxidize it. You'd have a similar bed over on the fuel side. Well, if you want to treat that like a stirred reactor, it starts to look like a conventional combustion problem. And the usual combustion design concepts apply here. The heat release rate, in here has to balance the incoming rate from cold reactants, or the thing will blow out. So that's how you would put together a design, just a mass and energy balance there, and that volume is going to be inversely proportional to the reaction rate. That's what I said before. That's why kinetics are so important. So you see where I'm going to go with this? It's conventional combustor, just first order design. How do I scale the thing when I know the kinetics? Well, you have to actually have the kinetics of the process, and I don't know how many people here are doing heterogeneous reactions and heterogeneous kinetics. It's a little bit different when you have to do a heterogeneous system. The common way to get started is in a TGA, so you put the sample on the pan, and then you run the temperature up, and then you just weigh the change in the weight of that pan, and that's how you get the kinetics. You just watch the reaction occur. In many ways, it's easier than doing kinetics on a gaseous system, right, where you got to track individual species. And for example, if you want to do the oxide reduction, you can just go back and forth with the sample on the pan, and we'll show you this in a second. But one of the complications run into is, what if I'm interested in coal? Right, I put the coal in the pan with it, and I run one test. Well, then what? You know, then you have to take the pan out, dump it out. You have to take the carrier out from the ash, put it back into the pan, and go through the next cycle. So people who are doing kinetics on those in this system, they're very patient. So if you see any of them, buy them a cup of coffee. They're going to need it, okay? But we've done it. And actually, the guy there, Tom Simone, he's emptied a number of pans and so on. But that's how you get kinetics in these systems. So let's take a look now at what some of these kinetics look like. This is an example of the TGA run where we took copper, and this was with a gaseous fuel with methane. And here you can see the mass on the TGA scale going up and down. Here we reduce, put the fuel in, the mass of the pan goes down as you take the oxygen off. And then you know, when you're done with that, you put oxygen in, reoxidize it, and then go through the cycle. And you can do a whole bunch of those and get a lot of good data because you just have so many repetitions. And then you just plot up the conversion. Remember I mentioned that, x versus time. And this is shown for, you know, a couple of different temperatures. And so you can see in, you know, the course of about a minute, even at that lowest temperature, we can get full conversion of the carrier back to oxygen. I think this is the oxygen. Yeah. I'm sorry, that's the methane, so it actually goes the other way. So that's the reduction step that I'm showing there. Do the same process for oxygen, and then you can, you know, just fit to kinetic expressions for the kinetic rate of either oxidation or reduction. And there's an example of one right there. So fit the data to those kinetic expressions, and then that allows you to go back in and, oh, didn't skip one. I wanted to show this slide just to give you a little bit of insight that these reactions, to me, surprisingly fast. All right, so I'm going to show you this movie. I hope I can set the stage while I get it started here. Before I turn that movie on, I need to actually leave there and find the movie because it didn't play earlier off the PowerPoint. Let me ask you a question. We're going to do this with a propane torch. So what kind of flame exists in a propane torch? Is it premixed, partially premixed, diffusion flame? You guys should know this, right? What's that? We can't be arguing about what a propane torch is. I'm sorry, is it now? Oh, the air ports are open. Let me show you. I didn't think this would be that. Here. Because you'll need to know this to watch the movie and make sense out of it. Okay? This is what the flame is. Oh! We're going to get another break if I'm not careful here.
There you go. You just want to, you want to use the real thing?
I was actually going to bring a propane torch. There we go. Watch the movie here. So here we go. Here's a little experiment. There's a propane torch that we're going to light. And those are just two copper wires that I put on a piece of wood. That's my basement, by the way. See what I do for fun. It's kind of sad. But so there's a torch, and that's a partially premixed flame. You can see there's some burning occurring up above. So the partial pressure of oxygen in that flame region is pretty low. Now, you tell me, what color is copper oxide? It's brown. What color is copper? It's that shiny color right there. See it? Watch it as the flame goes back and forth. You can see it, at least on the outer surface. I would argue what you're doing is you're reducing the copper oxide, and as soon as the torch moves away from it, it's sitting in air at high temperature, and it goes back to copper oxide. All right? So I just thought it was a great visual representation to see going back and forth between the oxide state and the reduced state. I'm pretty sure that's what's happening there. My basement is not the most scientific environment, but I just did that and realized, because I'd seen it when I was soldering something, and it dawns on me, hey, I know what I'm looking at here. Reduced state, oxidized state. Right? So I took that little movie. Also, I got a new camera for Christmas. You know, most people take vacation photos, but anyway, that's just what we do at our house. Okay, I better get back into the main talk there. And yes, I did want to bring the real torch, but I just wasn't sure how that would work here. So let's go back. All right, where are we? We're talking about kinetic rates. And if I can get down to where that belongs now, right here. So we know something now about kinetic rates. They're not super slow. We've measured them in the lab, and then what you can do, what I think probably all of you could do, just given a little bit of time, is just go through, take those kinetic rates, write an energy balance and a mass balance on a stirred reactor, define a conversion, which is, as I've defined it here, define an efficiency, which is the conversion going out of the reactor minus what's going in, divided by 1 minus the conversion. So it's going to try to get to 1 up here. So that's the efficiency of the so-called combustion in that reactor. And you can then plot the results up right here. This is the thermal balance running along this way versus reactor. Here's the reactor temperature inside that stirred reactor. And what this is saying is, as I convert more of that material, this happens to be for oxidation of copper, as I convert more of that material, I'm releasing heat, and so the temperature rises linearly with the conversion. That's why it's just a flat line moving along that way. This is the kinetic expression. All it's telling you is that to get to fully converting that material, to get further out this way, I have to go to a higher and a higher temperature. All right? Where those two guys meet, that's where the reactor is going to operate, right? This isn't any different than doing blow-off in a gas turbine combustor. Same problem, it's done exactly the same way. Now, the interesting point here is, I asked the question, does this thing have light-off behavior? Light-off, by which I mean, can you make it ignite and blow it out? Well, it doesn't for the example I've got here, right? Look at the temperature profile here. It's just flat. If I go over this way, there's not two solutions to the problem. There's no light-off behavior. But I'm telling you, there are cases we're looking at right now that have actually, they look more like that. There's two solutions, just like in any combustor design, where you can either have low conversion or high conversion, and so the bed will light off. All right? Now I'm waiting to see, we'll show you the reactor working, and we see that in practice, but I wanted to do this calculation ahead because I didn't want our operators to start the thing up and say, boy, this thing just is not working very well, and keep fiddling, and then suddenly, pow, big heat release rate, right, that I got to manage through a back pressure control valve and other things. You need to know this before you run the system. So I think these beds do have light-off behavior, at least for the exothermic beds. It's actually pretty typical of all chemical reactors that are exothermic. Do a time-lapse here. Okay, so I just, to sort of wrap up thinking about kinetics, I just put in some results from just a few weeks ago here. So how big do these reactors really need to be? Well, with the kinetics we've measured, and again, this is not, we haven't peer-reviewed these yet. We're just getting them in the lab right now. Again, things look pretty reasonable for iron-based. This is the 2.5 megawatts per cubic meter for the exothermic reactor. So for 100 megawatts, you need 40 cubic meters. And so I just drew that out graphically so you can see what they did. So that'd be a 100 megawatt reactor with that rate, and that's pretty reasonable. All right, for people that build power plants, that's a reasonable set of dimensions. So I'm starting to feel pretty good about it. And if I go down to copper, wow, it's even better. So again, my message is these numbers are looking reasonable for this as a technology. We haven't obviously built these yet, but that's what we're working on. So let's take a look here before our break at kind of the reactor and the system design for these type of technology. I've already described it. We have experience in fluid cat crackers. There's also a large body of experience in circulating fluid bed combustors, something more familiar probably to us in this audience. But I've noticed that the reactor design, it depends on fluidization engineering. I'm not sure many mechanical engineers or combustion engineers study fluidization. Anybody? Looking around the room here. Anybody got background? I know there's at least some of the Utah group is involved in this, but probably not anybody else. So it's an interesting area. I just want to touch on it real quickly. It's important, like I said, for large circulating fluid bed combustors. This is the Jacksonville Energy Associate plant down in Florida. Pretty well-known power plant, but it's a very large circulating fluid bed combustor. And you put coal and ash in there and fluidize it. That cyclone separates a lot of the material out. It goes in a circle like that to complete combustion. hot products are sent over to that heat exchanger, and then you generate power. A lot of experience with CFBs. Important point I want to make here, the recycled solids in these CFBs, the mass flow rate, the recycled solids mass flow rate is significantly larger than the flow rate of fuel that's going into the system, like 100 times. It's interesting, you don't realize that until you start to study these systems. Because you look at chemical looping and say, oh, I got only 3 or 4% mass of oxygen on that carrier going around the loop. Doesn't sound like enough. Well, it's not any different here. You got like only 1% or 2% of fuel going around the loop. Right? So we have a lot of experience with these systems, and I just want to make that point. Again, also here, one of the things about the system, because there's so much mass circulating around that loop relative to the heat release rate from that small amount of coal, the temperature is almost uniform in there. You're going to see that in chemical looping. I talked about the endothermic fuel reaction, like, oh, how many get the heat in there? Well, you don't have to. It's going to come over with the carrier because you got so much material going around. Turns out you just take your heat out of the air reactor. It's probably adequate. We're designing that right now. Go ahead.
What are the implications of that for granting your thermal mass of the planet?
Yeah, of course, this is a steam plant, so it's a little bit easier to manage that kind of an event because, what you're saying is you got all this heat coming out. You're right. You're going to have a hard time unloading all that heat, but it's not like a gas turbine where the spinning turbo machinery is directly related to it. There you got to worry about surge, and you can't just unload arbitrarily. By the way, that will be an issue for chemical looping, especially in smaller systems, because you're circulating a lot of material around, but you can just stop it and let it sit there, right? In these systems, it's not like a gas turbine where you have all that air, it's trying to drive the turbine, you can't just unload the shaft. So. Good question. I realized, in spite of many efforts, I still make mistakes here. That number is wrong, and I can't remember which way. I just saw that the other day. So if you're taking notes there somewhere, just cross that number out. I don't think it's 28,300 after the back end look. I saw that in there. I thought, did I skip a 0? But I wasn't able to check it before the lecture. But this is just a list of different research groups, the type of reactors that they're using. You can see they're all CFB, bubbling fluid beds, all the way on down the list. The number of groups building these up. The one at our lab is not in here right now. I'll show it to you later because we're just getting close to turning it on. But anyway, we'll take a look at that a little bit later. So just want to let you see there's a good citation here. You go in and look at all the different reactor designs that people are looking at. And then I said fluidization. It's not covered in most combustion courses. So I just got a couple of slides here to show you what fluidization looks like. And this is from some of my colleagues at NETL. They do a lot of work in modeling fluid bed systems. If you decide to work in this area, go to that website right there. You can get free software that actually is probably some of the best software around to do modeling fluid bed systems. But let's show what I mean here by a fluid bed. The insert that's a little bit larger is looking at individual particles that exist in a bed when it's fluidized. This is a bed of, imagine it as sand material. And what you'll see when I play this movie is you're going to supply air from the bottom and fluidize the system. Oh, can't do that. This one I think will play properly. There you go. Okay, so you can see what happens when you fluidize it. Things float just like it's on water. And if this is hard conceptually sometimes for people to grasp, once you add enough air, the friction between those individual particles is gone, so they don't support it. A shearing stress, it becomes like a fluid. That's why you call it a fluidized bed. And so you can make that material flow much like you would flow water or something else. And that's what you want to do in chemical looping, is flow that solid material around just like it was water. I guess you guys like the rubber ducky. I'll tell my buddy Sham there. Slide here. Okay, so let's see what this looks like, simulation and experiment. This one I don't think is quite in here. What you're looking at is a comparison for simulation of a chemical looping system. We'll get started here. Ah! Wrong one. My apologies. This one. Okay, there you go. So the sketch on the left is actually the simulation that we're doing of this chemical looping system. This is an air reactor running up in this direction. You can see those particles going up, separated out in a cyclone, dropped into this, which is actually a seal reactor, and then this is where the fuel combustion is actually occurring down at the bottom, and this is another separating reactor. If we were doing solid fuel, the idea would be to fluidize this reactor so that as that carbon is burned, the remaining ash, which is pretty small, pretty friable, comes out of the top of this reactor. You don't see it in this simulation. And again, this is a loop seal running around this way, takes you back down to the air reactor. My point on the slide is we have pretty good simulation capability to design these reactors. You don't always have good chemistry in them, but this is a hydrodynamic simulation. And you can compare it to, this is a one-to-one, this is a lab scale environment that we were running to do a validation of this. And it looks pretty good to me, but you see anything wrong between the two? Just check. What do you see noticeable? Any noticeable difference there? The level of the bed in the middle, right? It's off. And so, you know, I'm an experimentalist by training, so you can't resist sort of pulling the chain all the modeling guys will. Look at that, you know, you can't get the bed height even right, you know, you guys, you know. And to finish the story, we had the experiment set up wrong. We fixed the experiment, almost virtual agreement. You know, so we're really proud of the hydrodynamic capability. There's a question here.
That's the slugging in the transport reactor. Is that ever an issue with the kinetic rates on overall system performance?
Yeah, yes, it is, actually. You want to avoid that slugging. It comes from the geometry right in this region right here. You have to actually neck that down, and what actually happens is above the bed, you tend to push material out of the top of the bed, and it's sitting up in the gas phase, and you want at a controlled rate to entrain that into the neck down and bring it up. And so the way you solve that problem, which we actually had to do when we were designing a little bit more, is by changing the entrance region right there so you don't actually just, you know, get slugging. It is sensitive to that part of the design. It is a problem if you slug through that area right, because then the kinetics don't match. Anybody else? No? Okay. We're almost at our break here. I'll just kind of pound through a couple more here and get to 3:30. I'm not going to talk much about this. I want to throw the slide in to mention that Princeton University is a key ally in our simulation of multi-phase flow. My colleague Madhav Shamlal works pretty closely with Professor Sundaresan, and so I put this slide in. Wasn't sure if anybody from that group would be here today or not, but I won't spend any time on it. Let's look quickly at solid fuel combustion. Specifically, everything I've said today about chemical looping has been general. Talk about gaseous fuel, chemical looping, but I want to spend just a moment talking about solid fuel combustion. You know, we started this work a number of years ago, and I was really questioning whether you could get a fast enough reaction rate between solid coal and the solid carrier. How fast would they react together? So we put them in a TGA pan, and again, there's weight versus reaction time, and you know, the blue line is the temperature as you drive it up in the TGA up to the operating temperature of about 1,000 in this case. And so what we did first, we put coal on the TGA pan, drove the temperature up. You can see the volatiles coming out. We're doing that initially in nitrogen, and then we added oxygen, and you burn up the char. All right? And you can see the weight go down. So that makes perfect sense. You know, what you're seeing there on the TGA pan is just devolatilization, moisture out, combustion of the char that's left over with oxygen. And then we loaded the pan up with the same similar coal, but we put in a metal oxide. I think it would have to be copper oxide in this case. And then we just started heating it up. So the temperature going up. By golly, the things being consumed by the oxygen from the metal oxide, the atmosphere with pure nitrogen. So you're burning up all that carbon with the oxygen coming from the copper oxide. And then of course we reoxidize the copper right there when we introduce the oxygen, so the weight goes back up. Well, that all made sense, and I said, that's fine, we expect that to happen, but the rates were way better than I expected. And so my colleagues, we kept checking it, and we had a lot of arguments about why the rates were so high, and we just didn't know. So we started working on that a little bit. There are a number of reaction pathways that you'll see in the literature for oxidizing a solid fuel with chemical looping metal oxides. Obviously, you can just heat it up. You get pyrolysis products. For example, CO or hydrogen would then react in the gas phase with the copper oxide to make CO2 and water. The CO2 that's produced can then gasify the carbon, and then that CO2 in the gas phase can react with that oxide. So that makes sense. I'm sure that happens. You can also, conduct a process in carbon dioxide. So you gasify the carbon to CO, and the CO can react with the copper oxide to give you CO2. And then finally, a process, chemical looping, oxygen uncoupled. Look, if you heat up copper oxide high enough, you get above that equilibrium, it'll just drive the oxygen off, and then it'll just react with the solid fuel with the gaseous fuel. So that's uncoupled. And you could even do that with two separated, right? You could make oxygen just by heating up that metal oxide. The difficulty you run into is the copper oxide, in this case, it tends to get pretty soft when you get up to those temperatures where you're driving the oxygen out. So you get a lot of agglomeration. So how do you take that agglomerated material over and reoxidize? It's a problem. But then there's one more mechanism that's interesting, and all these are important. I just thought I'd like to talk about this one because it's so, well, it's interesting to me. I hope it's interesting to you with only 10 minutes before your break, but we'll go through it quickly and sort of wrap this part up. So you take metal oxide and react directly with the solid, the two solids reacting together. I didn't think that could happen, I'll be real honest with you, but we kept looking at the data we had, and we came to some conclusions. It must be happening. Here's why. So what I'm showing here is a plot of representation of some experiments that we did. And if you look at, we did these experiments at 500 centigrade, take copper oxide, the partial pressure of oxygen over copper oxide at that temperature is 10 to the minus 9. So we said, removal of oxygen down to that level can you actually make the reaction go significantly with that oxygen partial pressure? So, all right, let's go figure that out. So we started off and said, well, let's just take some air and go in at 500 degrees. So air has got plenty of oxygen. And we had a pretty modest reaction that we were seeing occur. So, all right, well, let's now take vitiated air, 2% oxygen, way more oxygen than up here, right? Lots of oxygen still, but it's vitiated compared to conventional air. It just sat there on the pan, didn't react. I mean, the reaction was so slow, you wouldn't even notice it. Well, the funny thing is, at that same condition, if we put these two things in the pan together, where the partial pressure of oxygen here is 10 to the minus 9, it just went like crazy. Burned the stuff up. Why is that? Well, the only conclusion we could have was they must be reacting together solid to solid, touching each other. Which again, I protested against that. I said, that can't be right. So we said, all right, let's do some other tests. Here's another TGA run. This time I'm showing the rate of reaction that we observed on the pans. That's how fast these things are reacting is represented here. Here's the temperature rise in the TGA. So it's loaded up with 100 micron size coal with these copper oxide particles. And what we ended up doing was changing the size of the copper oxide particle. All right, so we just kept grinding it out thinner, and what do you see, right? You get a higher reaction rate, earlier on at lower temperature as you get more intimate contact between those smaller particles and their large neighbors. I said, I'm still not sure I believe that. So we went on here. We said, well, let's keep the particles the same, but let's just separate them. So we took the same amount of material, but we diluted it with, I can't remember what the material was. It was a quartz that we diluted the material with. So for example, this was the original sample of carbon, copper oxide. Then we put in, times 5 as much quartz so that things would be separated and put it on the pan. And then 10 to 1. And sure enough, what you see is you have to go to a lot higher temperatures to get the reaction to occur. And it's a slower reaction, and you start to separate these particles. We're starting to piece together a little bit of a story about what was going on here. There's more to this. We ended up doing DFT calculations and showed all this. Anyway, we pretty much came to the conclusion, going over the paper, that these two solids actually do react together. Well, I'm not planning on building a reactor to grind up my coal and my oxygen carriers so they hit each other, right? That's not the point. But what occurred to us was, well, gee whiz, if I do have coking on the carrier, all right, it's going to be right next to the oxygen, the metal oxide, and it'll react. That's why I said before, I'm really not worried about coking with heavy fuels on these things. As long as I've got oxygen, the oxide state, I think it's going to show it up by this solid reaction. And believe me, we could talk all day on this. We've looked at it a lot. lot, and I think that's the right conclusion. And about the same time we were doing that, we didn't know this. We found this almost serendipitously. Mike Zachariah at University of Maryland was doing some similar studies, and then we ended up joining forces on this. So what he is doing here, just to make that same point, that you have this solid phase reaction, this is an experiment that he runs called temperature jump mass spectroscopy. The image that you see through here is a wire, I think it's like about 50 microns, that he can apply a voltage to, so you get really rapid heating. And then what he does, he puts solids on that to study their reaction on that surface, and he has a mass spectrometer that looks at the material that's ejected from that reaction. And so you can actually track that reaction, drive it very fast with heat from this wire that's in the middle of the thing. And here's what he found. He started off here, let me find the right one here. This is just a plain copper oxide coating on the wire. And what he tracked here was the oxygen coming off that wire. So you can see there's two runs here just for some repeatability. You can see the oxygen starts to emerge out here after about 2 milliseconds. But when he put copper oxide together with solid carbon as the coating, he starts heating that up, and you see CO2 coming off before the oxygen even had a chance to get out of that metal oxide. Does it make sense to you? It's likely those metal oxide are reacting together in that environment. I can't think of any other explanation for the data. He made a nice movie of that, and I'll show this, and then we're going to wrap up here before our break. So it's just fun to play. We'll play. Won't play. Not that important. What you would see is just... Is it going? There you go. Okay, you can see it. And you can see the material disappearing off the surface of the wire. It is a great experiment for understanding heterogeneous chemistry, because he can watch those species as they fly off that wire when he does that heating. So my hat's off to him. We are working with him today on understanding some of these processes even more. It's just a minute or two before 3:30. I'm going to skip a number of these slides because we're going to switch to a different topic when you come back from the break. But I've just tried to give you a broad overview of chemical looping. I wanted to say that our lab is very active in this area right now. We have this project called Industrial Carbon Management Initiative, where we're developing chemical looping combustion as a technology for industrial applications. We're also looking at taking the CO2 from that process and using it geologically to enhance the recovery of natural gas from shale deposits. Something that's not really been done before, but we're seeing that 20 years from now, when they deplete those by primary production, we've got an infrastructure where we can probably get even more natural gas if we had CO2 to inject. So we're already looking at that, and I've talked with one individual in the audience interested in our work on photocatalytic conversion of CO2. Not going to have time to cover all that. Just want to let you know we're actively working in these areas, and so if you're interested, come talk to me. I'd be happy to talk to you. Let's take a break. We're going to come back and then jump to the next section. So I think, how long is a break, anybody? 30 minutes? Is that how we do it? Okay, good enough. Thanks.